And you recognize that.
Yeah, that's the globe of the Earth.
That's supposed to represent the Earth, right? And if that's the Earth, what's this thing?
That's the moon.
Right, going around like that. And what's that?
That must be the sun.
Right. Now there's 93 million miles between the Earth and the sun, so obviously the scale is not correct. But the reason I wanted you to take a look at it because I wanted you to sort of realize sort of how they're all interconnected in terms of their movement. How long does it take that to make one revolution?
24 hours or 1 day.
1 day. Now it's at the same time it's going around the sun. Move it and have it go like that, right? How long does it take to go all the way around?
It takes 365 days.
Yeah, a little over. Yeah. Now the Earth doesn't go backwards like this, but let's move it backwards anyway. How long does it take the moon to go around? Do you know?
No, I don't.
About a month, right? That most people realize.
Yeah.
When you see on the calendar, it's actually 28.25 days, or a little more than 12 times going around the Earth, 12.9. Anyway, by the way, if you were living right here on the Earth, it'd be daytime, right?
Yeah.
Could you see this moon if it's there?
No, I don't think so.
Why is that? Because you don't think you see the moon during the daytime? It's there. If you look for it, you'll find it.
You will?
Yes. You look up in the sky in the daytime, and if the moon is supposed to be there, it'll be there. Don't worry.
Oh.
You, however, see it mostly at night, right? And as it moves around like this, it goes through various phases. It's hard for us to see it in this thing. So this moon, instead of moving now, is going to be this stationary ball.
Okay.
And the sun does not ordinarily move in the sky. You know, the Earth and the moon move around it. But I'm going to be the sun with a light.
Okay.
So I'll move and the moon will stay still. You go out there and look at this as the moon. And I'll go here. I have a spotlight which will be the sun. And as soon as I turn it on, then I'll give you the night sky. I'm going to turn down the lights now. What do you see?
It looks like about a quarter moon.
Yes. Okay, now I'll slowly start to move around.
It's almost a half. Now it's a half moon. And 3/4. And now it's a full moon.
Okay, now, in order to continue, I'm going to have to sink the sun lower in the sky so I can move in front of you so I won't block your view. Okay, do you see it?
Yeah. And now it's starting to get smaller again. 3/4, a half moon, and 1/4 moon.
Okay, almost the end?
Yeah, almost.
Okay, I'll turn on the lights again. And so I can turn out the sun. There. So come on in. So you'll see those same phases of the moon like that, even in the daytime sky, because it's going around and around the Earth all the time, right?
Right.
Okay. Well, next time, take a look at both at night and the day to see the phases of the moon, like this. Nikki, you noticed the difference when you're swimming at the top of the water and then down at the bottom of the pool?
Yeah, when you're swimming on the top of the water, well then you feel like a hand or something is holding you up and you're sitting
Pushing
on
you from
top
below,
of it.
right. Yeah.
Yeah.
And at
And
the
when
bottom?
you try to go down, something is sort of trying to keep you up there.
Well,
like
again, you're floating. In other words, you're sort of like a cork. You put a cork
Yeah.
below the water and it comes up. But it's one of the things that I think is sort of strange is that the reason why the water is pushing us is because of all of the weight of the water. And weight's pushing down, right?
Right, so if it's pushing down, well then you
Why-
should go down farther.
Why you go down further? As a matter of fact, the idea is that, well, here, let me see if we can illustrate it. Here's a lamp chimney. You recognize those?
Yeah, my mom has one.
What does she do with it?
She
Puts
has
a
it
candle in
this
it?
way and
Oh, okay.
has the kerosene
Well, I have it upside down, and I have a jar cover here like this with a piece of string, see? So you hold that, okay? Now I'm going to put the whole thing down underwater, and you watch what happens. Okay, now you can let go of the string, and look. It
It's
isn't
filling
falling.
up.
Yes, it's filling up because there's water leaking in. Now notice it went down? Did you notice the level of the water inside when it dropped?
Yes, it was up to here.
The same as the water.
Very edge.
What now? So can you explain now what happens?
Well, the water, when it's only up to here on this thing, isn't,
Right.
the weight pushing down isn't enough to beat the...
To beat the pressure pushing
Yeah,
up, right.
push-
So obviously it must be pushing up.
Right.
Right.
Has to be.
Okay. Then what happens when it falls?
When it falls, it's because the weight, the pressure pushing down is as strong or a little bit stronger than the stuff, the pressure that was pushing it
Okay,
up.
let's try it again now. You know what to do. Ready? Hold it in nice and tight, because here we go. First down. Okay, you tell me when it's going to go this time. Now?
Nope.
Now?
Nope. No.
There you go. Very good. Now you understand that when you're under the surface of the water pressure is pushing you in all directions, up, down, and every way. Right. The high mountain country is where Colorado Wildlife Division biologist Rick Hoffman comes to observe and capture blue grouse. Not much was known about the bird's winter habits until this study was begun. A blue grouse is located in a tree. He gets ready to capture it with a noose at the end of a pole. Most blue grouse remain motionless, relying on their coloration to avoid being seen. The bird is brought down quickly so it can be released without being injured by the noose. The bird is kept in a bag until they're ready to put an identification band around its leg. They capture and band more than 100 grouse each year. A bird can also be fitted with a radio collar that goes over its head. After release, the grouse will be tracked by radio. The conventional battery in the radio collar will last up to 1 year. The scientists also observe birds in captivity and offer them various kinds of food. The bird's preferred winter diet seems to be only the needles of Douglas fir and lodgepole pine trees. The new information will be useful to those who manage the state's forests and regulate the hunting of the popular game bird, the blue grouse. Fonda, I made this out of a piece of leather, but you could make it out of a stiff piece of paper, couldn't you?
Yeah.
Okay. Now, what would you do?
Well, I would cut a rectangular shape like this, and then fold it over, and cut 2 lines so that now there's a strip in here.
So that you have a strip in the middle, okay? Then what?
Then I would put a piece of string in here, punch a hole, and put the 2 ends of the string in here, and tie buttons onto them.
Well, you'd tie the buttons on after you got the string through the hole, obviously, right?
Yeah.
Well, the reason why I wanted to make this is because it's an example of a popular puzzle in which you have to get the buttons and the string off of this piece of leather, or in your case, a piece of paper. And you made it a hole small enough so the buttons won't go through. But this little strip that you cut out here would go through the hole, wouldn't it? Yeah. So if I put the strip through the hole, you pull on the 2 buttons now. Keep pulling. There. Now you know what to do?
Yeah. Now you can fit the buttons in here
Right.
so they come out.
And now you got it off without cutting the string. So put it back on again. You don't have to untie the buttons or cut the string or get a new string, right? All you have to do is put the leather through the hole, or in your case, the paper, and
Fit the buttons in.
okay, and put it back, and there you are back again. So if I give you this, I'd like you to try it on your dad, because I don't think he'll be able to get it. Deal?
No.
I don't assume that you've ever been a chemist, have you, Brenna?
No, I haven't.
Well, today you're going to be a chemist. You're going to help me find out whether antacid tablets really work.
Okay, how are we going to do that?
Well, we're going to use the universal indicator, but first, see that knob?
Yes.
We'll turn it on. This is an electric stove, but we're not using the heating part. We're using another sort of hidden part. See it?
Oh, look at the magnet. It's spinning around.
Underneath is a magnet spinning, and that makes this magnet spin around. And so
Look
Look at the little tornadoes.
Yeah, that shows that it's spinning around. And chemists use this so they don't have to stand and stir something.
Yeah.
Now we're going to add some universal indicator. I'd like you to put in 24 drops. And I'll tell you about universal indicator in a moment. Now you have to be very precise. You get exactly 24 drops in there. 1, 2, 3.
4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24.
24. Fortunately, it's not that critical. I think you may have had an extra drop or two there, but it's all right. Now, remember I told you that was a universal indicator. See the color?
Yeah, oh, it's yellow.
Yeah. Now, here's a chart that I made up for you. See if you can understand. Scientists call the test for acidity or something that's basic pH. And the smallest numbers are the most acid.
Oh.
And with our universal indicator, see the color?
Red.
Okay. Now we're going to get less acid and less acid. You see what happens to the color?
Yeah, it goes all the way from red down
Orange,
to blue.
yellow,
Green.
greenish, and blue.
Yeah.
And down here we're quite basic.
Yeah.
So we can tell by looking at the color whether we're counteracting the acid or not. So far we haven't added any acid. In view of your miscount, do you mind if I do the acid?
No.
Okay. One, 2, 3. I think I was as bad as you are. I miscounted too.
Changed colors.
Yes. So now you saw, remember in that chart, red was the most acid, right?
Yeah.
Okay. Now, here are antacid pills. So put them in there.
These pills are supposed to
still
make
the
the
same.
acid go. and
Right, that's supposed to make the acid go away. But you must remember, the stomach acid is very important because that helps you digest food. And you want your acid in the stomach. But sometimes people get too much, they think, and so they sometimes call it heartburn. And they feel a sort of aching, and so they take these antacid pills to sort of counteract it. So we can find out now whether it really changes stomach acid from an acid to a more basic. You see any change?
Well, it used to be
as red, is it?
red. Yeah, it's a little
more
orangey.
orangish?
It's turning paler and
Paler and paler? Well, keep an eye on because once it happens very quickly. There
Oh,
it goes. Look
there
at
it goes.
Yellow,
Yellow,
Green.
green.
greenish blue.
Oh, yeah, it turns into, goes really fast.
Right. So, as a chemist, would you say that stomach acid counteractors like antacids really work?
Yeah, they do.
Good. Ben, see, I have a funnel taped to one end of 50 feet of garden hose, and you have the other end there. You hold it in the bucket because I'm going to pour water in here, and I want you to predict what's going to happen.
What I think should happen would be water coming down the funnel into the hose, then round and round and round, and then it'll eventually come out into the bucket.
Okay? Let's see if your prediction is correct.
How comes the water's not coming out?
Yeah, look, and I'm not only that, but I'm filling it up so that the water is coming out the funnel and no water is coming out the other end.
I know. How come?
Well, that's because I call this a mysterious garden hose. And in order for you to understand why it doesn't come out, come on inside to my workshop and I'll show you. Ben, this is my sort of homemade version of the garden hose out there. Remember, there was a funnel.
Yeah.
And it was down into tubing. In this case, I have transparent tubing so we can see what's going on inside.
Great.
And I poured water in, right? Mm-hmm. In this case, I'm going to pour red liquid. Okay, why is the water going down?
Probably because about the force of gravity.
You know, gravity is pulling down on it, just as you'd expect. And you remember, I kept pouring. Now, see what's happening?
The funnel, the fluid in the funnel is
Getting higher and higher. And see what's happening to the water in the tube?
and the water's coming round and round, but slow.
I better stop now before it flows over. Why isn't the water going down now?
Probably because about the pressure in the...
There must be
Loops.
pressure of some kind in that
Yeah.
hose, right, to keep it from going. In fact, if you did some measurements, you'd find that the column of water from one side to the other equals the column of water from here down. In other words, you add up all the pressures. I'm going to raise it now. Watch what happens. As I increase the pressure over here, we're going to get equal pressure on the other side by the water moving in the tubes.
Neat. The water's moving down
Yep.
more and more.
See if I can finally fill up. We have 4 coils here, while outside we had 16.
That means the...
I'd have to really go higher than the trees in order to equal the pressure that we would have inside, right? So what did I call this?
I think you call it the mysterious garden hose.
I guess I can't call it that any longer, right?
I guess not.
The race started out on land, but watch. They head right into the water. They can actually sort of float over almost any kind of terrain, and that's why they're called hovercraft. A fan mounted in front of the windshield forces air down and under while the rubber skirt keeps the air from blowing away. The result is a cushion of slightly pressurized air. That's why they're also called air cushion vehicles. The fan at the rear moves the vehicle forward. Rudders are used to change direction. Ohio State University documented a regional race that included an engineering student who built one of the unusual vehicles that can travel over almost any surface on a cushion of air. Okay, Brian, would you put your 2 fingers up like that?
Okay.
I'm going to put a loop of string over that one and over that one. And as you can
Ew.
see, in the center of the loop is a washer. And the trick is to get the washer off of the string without cutting it or without taking it off either one of the fingers.
Oh, it seems impossible.
It does, but here's what you do. I'm going to do it very easily by putting 2 loops on that one so I can take one off, right? Then watch what happens.
Neat.
Yeah.
It's amazing.
Now, it's based on the idea
you do
that even though you're taking the loop off the finger, it doesn't look like it. And a lot of string tricks are based on that. Okay, here, you do it on me. Take the far string like that and put it over that finger, but way down. That's it.
Okay.
Now you have 2 loops. Now you can take the top one off and get ready to catch the...
That's
Very
neat.
simple. Who are you going to try this on?
I think Danny.
Oh, your brother, Danny?
Yeah.
Okay, so let's do it once more to make sure you get it. And I think you'll probably fool him, too.
Okay.
Take the
so
far one. Now you
take the
tell me
far
what to do.
one And put it over his finger way down. And take the top one, slip it off. There it is.
Very good. Hope you can fool Danny okay.
Yep.
Sam, that may not look like it, but that's supposed to be a swimmer.
Oh, okay.
A medicine bottle with its head right here, and then I put clay in it to weight it down, and then the 2 arms are clothespins, but they're raised. I'd like you to put the swimmer in the water.
Okay.
Notice that he floats.
Yeah, but only his hands are out over top
Yes,
of the
only
water.
his hands are under. But the point is he floats. There's enough to him that he displaces enough water to float.
Okay.
This would be true if a swimmer were in trouble, for example, and he wanted to raise his arms to signal for help. At the time when he does that, he's going to sink down into the water, because now I'm going to put the arms down along his sides,
Okay.
like that. Okay. Now put that one in the water.
He floats higher now.
Yeah.
His
Well, you can
head's
see the
over
things.
the water.
Well, because his arms are down below, displacing water when they're next to his sides,
Oh,
just like they did
see.
up above. And now his head is out of water. So it's a good idea if you're trying to float in water to keep your arms down along your sides. because then you will displace more water and float with your head above the water. Try it next time you're in the swimming pool.
Okay.
Well, okay, there was 25 in one row, and there was 8 rows. That's 200. And then with the 4 extras, it comes out to 204.
So that's our estimate using, you can see why I call it the box method.
Yeah,
it's
'cause it's in a
top,
box,
right?
yeah.
And you could even have a couple of layers, couldn't you?
Yeah, you
in
could
order
have
to estimate.
4 or 5
What we're
layers.
trying to do, of course, is to estimate the total number of balls here. And it's very similar to in school where you have a whole big bunch of beans or something and
Yeah,
you try to
in a
estimate the
jar,
total
yeah.
number. Okay, let's put them all back.
Well,
And notice what the next one is.
yeah, it's the volume method.
Okay, wait a minute.
Well, there's the blank balls in 100 milliliters.
Like that.
So, yeah, like this. Since
Okay.
that's 100, it goes up to 1,000.
Okay, so let's find out how many balls make a
Okay.
volume of 100.
Okay, there's 5,
10,
15,
20.
25.
Wait a minute.
Yeah, that's about right. Maybe a couple more balls.
Well, put in one.
Let's see what that equals. Yeah, that's level.
Okay, now what does it say here? How many balls in 100?
Well, it says, well, it'll be 26 balls in 100.
Now all we have to do is get the total volume of all the balls, right?
Right.
Okay, you want to pour?
Okay.
I'll help guide him in here. Okay. What's the total volume?
Well, it's about 750 milliliters.
Okay.
Okay, if there's 26 balls in 100 and there's 750 milliliters, then you'd have to multiply 26 by 7.5.
All right, this is 7 times as
Yeah,
this, right?
7.
Okay, so what do you got?
Well, I've got 195.
Okay, so write that in there. Tyler, you have a small problem now. You got 204 here
Up top,
and
and
195.
Which one is right?
Yes, which one is right? In fact, this is typical of a problem that scientists face all the time, in which they want to find out the total number of mice in a field, or total number of molecules, or the total number of people doing this, that, and the other thing. They don't want to count every one, and they have to make a sample. And they have to devise methods of making sure that the sample is as accurate as possible representation of the whole. And it's a whole branch of mathematics called statistics. How are we going to be sure how many there really are?
Well, you'd have to count them like 1, 2,
Wait,
and
no,
then it
we
would take
don't want to
forever.
do that. I'll show you another way that we can do it. And by the way, they might use this system in a factory where they wanted to be absolutely certain of the number. Here's a trough, see it?
Yeah, okay.
Okay. And down there is a light.
Yeah, I see
And
it.
if you roll a ball down the trough,
Yeah.
here's a counter.
Okay.
Is it 0 now?
Yeah, it says 0 now.
Okay, roll a ball down there.
1.
1.
It counted
Here's
the ball.
3. What should it read now? 1 and 3?
Well, 1 and 3 equals 4, so that
Okay.
number down there should be 4.
Very good.
4.
All we have to do is do the total number right, huh?
Okay.
Here we go. Hold up that thing so I can pour. How many we got?
Well, we're at 40, 50, 60, 70, 80, 90, 100, 11, 12, 13, 14, 15, 16, 17, 18, 19, 200 exactly.
Yes, that's exactly the number that I put in there in the first place. So you see,
Okay.
the really only accurate way is to count every one. But using modern technology, you can do it very quickly.
Okay.
And in a factory, if they wanted to count exactly the number of BBs, for example, they could use this system.
Like when they package
And if
it.
not, they have to use a branch of mathematics called statistics and a technique called sampling, which you just did. Very good.